Hello, welcome to a Solidworks tutorial for design. This video will cover the essential topics for equations and how to design with them in mind. Equations are a very useful skill to know while CADing, and if done right, they can save you a lot of time in robotics. So let's get started. To put it simply, equations are a Solidworks feature that allow for a relationship between dimensions. For instance, if you wanted to link one dimension with another through a mathematical operation or equality, you would use an equation. Equations are important in the context of CAD since they allow for flexibility in designs and enable designers to CAD a general case of a part. For example, it is much easier to CAD the general case of a gear with the number of teeth, diametral pitch, width, bore size, and so on as variables driven by equations as opposed to re-CADing a gear every single time. The equations menu can be accessed by right-clicking the feature tree, clicking hidden tree items, and then equations and manage equations. This will bring up the equations menu for you to enter your variables and values. If you wanted the equations icon to show up on the feature tree every time you create a new part, right-click the tree, click hidden tree items, and this time click hide and show tree items. And under the equations icon, click show. Another way is to configure a keybind or a mouse gesture to bring up the equations menu. For me, I have it set to when I move my mouse to the bottom right, it brings up the equations menu automatically. To do this, you can go under the option Customize in the Settings tab, and for keyboard gestures, you would search up for the equations and then enter a shortcut, or under mouse gestures, and you can see here that I have my equations shortcut set to my bottom right hand corner. In the equations menu, there are three tabs. Global variables holds all of your numerical values or equations that you define. You can reference other global variables inside a global variable, but you must define the one that is being referenced above. For example, if I had two variables a and b and I wanted to set b is equal to a divided by 2, I would first have to define a above b. Features is where you can define certain conditions to either suppress or unsuppress a certain feature in your CAD. I'll go over this later on in the video. And lastly, the equations tab. SOLIDWORKS typically handles this, so you really shouldn't ever have to manually enter equations into here, but it's basically where the equations you define in your sketch go. Now that we know what equations are, let's use them to CAD a simple hex spacer whose inner diameter, outer diameter, and length are all equation driven. Under global variables, type in the name of the variable that you want to describe. So let's first do the inner diameter. Next, set that equal to a value. For now, let's set this to 1/2 inch, and to create a 1/2 inch hex spacer. Note that this inch sign here is completely optional. The only difference it will make is when you change the units of the part. Variables that are defined by the units will stay, whereas those that aren't will convert to the new system. In this case, if I remove the inch and set this part to the metric system, the inner diameter will then become 1/2 millimeter. If I add inch at the end though and switch to metric, the inner diameter will then be 12.7 millimeters or 1/2 inch. Its value gets preserved. Now let's do the same thing with the outer diameter. Let's set this equal to 1 inch. And then the length. Let's set this equal to 1/4 of an inch. The equations tab here is completely optional, but it allows you to define something. So this is the inner diameter. This is just for helping you in the future understand what these variables mean. Click OK. Now that we have our variables defined on one of the planes, let's begin sketching. First, sketch a hexagon that is circumscribed by a circle. In the hexagon, using the Smart Dimension tool, let's link this variable or this dimension with the variable. To do this, we first add an equal sign in front of the dimension. This tells SOLIDWORKS that you want to link this with a variable. If you don't remember the name of the variable, you can hover your cursor over global variables and it'll specify all the variable names. So in this instance, we'll set this equal to inner diameter. Once you have that set, SOLIDWORKS will add a red sigma summation sign in front of the dimension. This is to tell you that this dimension is equation driven. Now let's do that with the outer diameter. So now we have our sketch fully defined by equations. Now let's extrude boss base this. Similar to the sketch, we can type an equal sign, and then on our global variables, we set this equal to the length. In some features though, however, Solidworks won't allow you to enter an equation. If that's the case, you would enter a placeholder value such as 0.25 inches. Click the check mark, and then click the feature, double click the dimension, and then it brings up this menu where you can specify the equation driven. So in this case, you want to set this equal to length. Now that we have a spacer that is entirely driven by equations, we can change the variables to get spacers of different sizes and lengths. For instance, if I set the inner diameter to be 1/4 of an inch, the outer diameter to be 1/2 of an inch, and the length to be 3/4 of an inch, and click OK, Solidworks will automatically update. So now instead of recatting the spacer over and over again, we can simply refer back to this CAD, make the appropriate adjustments, and then click Save As. Solidworks also has a multitude of built-in mathematical functions such as sine, cosine, square, square roots, and so on for more complex equations. An interesting application of this is to prove the Pythagorean theorem using Solidworks. In a new part in the equations menu, type A, B, and C. A and B will denote two sides or the legs of the right triangle, and they'll be arbitrary numbers. So for now, let's set the equal to 3 inches and 4 inches. For C, we want that to be equal to the square root of a squared plus b squared. That's from the Pythagorean theorem. If you wanted to view all the available functions Solidworks has to offer, you can hover your cursor over functions and it will bring up all the trigonometric, log, square roots, sines, if statements, all that good stuff. But we're interested in the square roots, so to do that, let's first type in S and Q. You'll see Solidworks suggests the function called SQR. That's the square root function. It'll return the square root of any number inside the parentheses. So inside we want to type a squared plus b squared. To do this, first type a, surrounded by quotes, then the upwards caret notation, and then 2. This signifies a squared. It's important that you surround a and b with quotes, otherwise Solidworks will treat it as a number or a constant and throw an error. Press tab to evaluate it and you'll see it should equal 5 exactly. So press OK. Now in a sketch, you want to draw a triangle and make it an arbitrary triangle. So we make sure that no two sides are perpendicular or are orthogonal. On 2 of the sides, we want to set it equal to A. So we'll set that equal to A. We'll set this equal to B. And we'll set the third side equal to C. You'll see that it looks like a right triangle. To confirm this, we can smart dimension these two legs, get 90 degrees, and make this driven. And voila, this proves that Pythagorean theorem holds. If we change the values for A and B to 2, for instance, and something like 10, and we update it, you'll see that C has updated to be 10.2, and that this still remains 90 degrees. And that's the Pythagorean theorem using some of Solidworks' built-in functions and equations. One of the special functions Solidworks provides is the if statement, which tells Solidworks to prioritize one dimension over another in certain cases or suppress a certain feature. The if function listed here takes 3 parameters. The first is a condition that must evaluate to either true or false using one of the equality operators listed here. If the condition evaluates to true, then Solidworks takes the second parameter here. And if the condition evaluates to false, then Solidworks takes the third parameter here. This allows for certain features or dimensions to be prioritized under a specific case. And let's illustrate this with an example by catting an Allen key with an if function. Let's say that I want the hex size to drive the dimensions of the Allen key, whose length is 10 times the hex size. The handle is half the length, and the bend radius is 20 millimeters for hex sizes that are less than 20 and 30 millimeters otherwise. So here I've created a new part. In the equations menu, let's start off with defining our global variables. So since the length, handle, and radius is based off of our hex diameter, we know that the hex diameter is therefore the driving dimension for our Allen key. So let's first start with that. For now, let's set this equal to 10 millimeters. Now, for the length, we know that it has to be 10 times the hex diameter. And we know that the handle has to be half of the length. The radius, obviously, we're going to use an if statement. So for the radius, let's set if use Solidworks' built-in function. And we want it to be 20 millimeters if the hex diameter is less than 20. So that is our condition. If the hex diameter is less than 20, then we want it to be 20 millimeters. If not, then we want it to be 30 millimeters. And you'll see that SolidWorks correctly evaluates it to 20, since 10 is less than 20 millimeters. Now let's go ahead and CAD our Allen key. So we'll set this equal to the hex diameter. And then on the front plane, we'll CAD the path of the hex. And then use SolidWorks' swept boss base to generate the Allen key. So this will be the length. This will be the handle. And this will be the radius. Now when we use swept boss base, select this piece, we get our Allen key. And when we change the hex diameter, so right now it's 10 millimeters. Since 10 millimeters is less than 20 millimeters, it evaluates to 20. If we set this to something greater than 20, so for instance 25, it'll evaluate, the radius will evaluate to 30 millimeters. And that's what it does. And so we do that, our model scales accordingly. Another application of the if statement is to suppress a certain feature. Using the Allen key from the last practice, let's say we wanted to have chamfers on the hex faces, but suppress them when the diameter of the hex is less than 10 millimeters. So to do that, first we have to CAD in our chamfers. We'll keep it at 1 millimeter. And we want this to be suppressed when the hex size is less than 10 millimeters. And so to do that, we go to the Features tab. In the first column, you want to select the actual feature. So in this case, that'd be chamfer 2. Here, you want to add your if statement. So if we want hex diameter is less than 10 millimeters, then we want it to be suppressed. So suppressed or unsuppressed. And you'll see that in this case, it is not suppressed because 10 millimeters is equal to 10 millimeters, not less than. If we set this to 5 millimeters and have everything update, then you'll see that the feature is suppressed and it doesn't exist. And if we have it set to 30, then the chamfers are unsuppressed. And that's how you would use if statements to suppress and unsuppress a feature. So to recap the key major point, equations are great at making CAD flexible and efficient. Instead of recading the same design over and over again, equations allow you to create a flexible base case which you can use as a generalization. But they are difficult to master and fully incorporate into designs. The only way to improve is through practice, so I encourage you to go out and practice CADing with equations. It's the only way you're going to get better.